Hello, thank you for watching this video. So in this video, we'll be doing question 8 of November 2023 question paper mathematics paper 2. And this is the Euclidean geometry. So I'll read these questions and try to answer them. So let's go. In the diagram, O is the center of the circle. So we're given this diagram here, and we're told that O, which is this point here, is the center of the circle. No problem. So they're saying use the diagram to prove the theorem which states that the angle subtended by the chord at the center of a circle is equal to twice the angle subtended by the same chord at the circumference of the circle. That is proof that angle O is equal to twice angle K. Let me try to read this again. They're saying in the diagram, O is the center of the circle. So we have this diagram here, and this point O is the center of this circle that you can see. No problem. They're saying use the diagram above to prove the theorem which states that the angle subtended by a chord at the center of a circle is equal to twice the angle subtended by the same chord at the circumference of the circle. That is proof that the angle O subtended by TP is equal to twice the angle K, which is that angle there, subtended by the same TP. So, what these people are asking us to prove, they are saying now, we must show that angle O, which is this angle here, subtended by TP. You can say TP, TOP, which is angle O subtended by TP, right, is equal to twice angle K, which is subtended by the same TP, which is angle K, which is subtended by your TP. That's what they want us to do. No problem. So the first thing that you need your own construction on this thing, right? So let's have our own construction. So just say construction here. So what do we say here? So I'll say, let's draw a line, KOD. I'm drawing the line KOD, where D lies inside the circle. That's what we'll do first. The first thing that we do, we'll draw a line KOD, where D lies inside the circle. So here's K, here's O, and D is somewhere here, but inside our circle. Let's try to do that and see how that goes. So K from here, let's say maybe D is here. Here's D over this point over here. So I'm trying, this dotted line, try to think of it as a straight line, right? Try to think of it as a straight line, KOD. So I've drawn the line KOD. And immediately after drawing this line KOD, you can see that if you look, you can look at this in pieces. The first piece, let's look at triangle KOT. Let's look at triangle KOT. Look at this red triangle. I'm going to call KOT as a red triangle because two sides are red, right? So look at KOT there. If you look at your KOT, you can see that this side is equal to that side. Because OK, which is this side, is measured from the center, is joining the center of the circle to that point K, which lies on the circumference. So this is the radius. And OT, the distance from O to T, is measured from the center of the circle to the circumference is also a radius. So it's obvious if you look at this that your OK and OT are equal, right? So you say, okay, my OK and my OT are equal. I'm going to use a red ink to represent that I'm looking at a red triangle. So let's just say triangle is red, right? KOT. You can see in triangle KOT that your OK is equal to what? Is equal to OT. Why? Because those are radii of your circle. Radii is a plural for radius. You don't say radiuses, you say radii. No problem. So your OK and OT on the red circle, OK and OT are radii of the circle. So they are equal. And if you look at the same triangle KOT, you can see it looks like this. I can say it looks like this now, with two sides equal, right? So this triangle is called an isosceles triangle. It's called an isosceles because this side and this side are equal. So here is a triangle. So you have an isosceles triangle. And you know that on your isosceles, your base angles are equal, which is this angle is equal to that angle. Because these angles are angles opposite equal sides, because this is, so if you're looking at this angle here and this angle there, so this angle is facing that side, which is the radius. And this one angle here is facing that same side, or sorry, not the same, the other side, which is also the radius as well. So these angles are base angles of an isosceles, right? That are facing opposite equal sides. So these angles are opposite equal sides, which are both the sides of the radius of the circle. So both of those angles are equal just by looking at this triangle of yours, because this is an isosceles similar to this one. So from this, we can conclude that this angle T and angle K are equal. Why? Because these are angles opposite equal sides, because they are opposite equal sides. This one is equal to the radius and this one is equal to the radius. So if you have a triangle and you have two equal, with a triangle, if you have an isosceles triangle, the base angles will be the same. So in that case, what do we say? We say, okay, our angle, which is what? Which is OTK, which is our angle T, is equal to what? It is equal to TKD. Why? Because these are angles opposite equal sides. These are angles opposite equal sides. You can see that this angle is equal to the radius and this angle equal to a radius. So you have an isosceles triangle, and you know the base angles of an isosceles triangle are equal. No problem. This was a red triangle. If you look at the green triangle, you see exactly the same thing. If you look at this green triangle over here, you see that this length OK is equal to OP. Same reason, because the OP is measured from the center to the circumference. This is the radius. Center to the circumference, that is the radius. So you can say that in triangle, what? Say KOP, in triangle KOP. So you can say that your OK, I'm writing green because I'm looking at the green triangle, is equal to what? Is equal to the OP. What's the reason for that? The reason is, you can say these are radian. Because OK is a radius and OP is a radius. So they are radian. That's what you can say. Then, from that, you can see that these two are equal in this triangle, KOP. This angle is equal to this angle over here. Because we have an isosceles triangle, and you know the base angles of an isosceles are equal. So this angle is equal to that angle, because this angle and that angle are facing equal sides. These are angles opposite equal sides. So therefore they are equal. So what do you say? You say this angle over there, which is what? Is D, K, let me write them. This one will say D, K, P. So D, K, P, that angle K there, right, is equal to what? It is equal to this angle over here, which is KOP, which is equal to KOP. How do you reason for that? You say these, this is not KOP, is KPO, right? It's KPO. How do you reason for that? You say these are angles opposite equal sides. So these are angles opposite equal sides. No problem. Happy with this? Yes, I am so far. I will not restart, or maybe let me restart. So first thing that we did, we drew our line KOD, which is because we made our own construction KOD. No problem. And we said that our D lies inside the circle. No problem. And then we looked, after drawing KOD, we looked at the triangle KOT, which is KOT, right? And we concluded that your OK is equal to OT because both of them are radii of the circle. And the second thing, we said this angle and this angle are equal because they are the base angles of an isosceles. Or you can simply say that or you can just simply say they are angles opposite equal sides of a triangle. So they are equal. It's the same argument there as well. You look at the same triangle KOP and you say your OK is equal to OP because they are both radii, right? And then you say your angle K, which is this angle here, D, angle formed by KP, is equal to the angle P, which is formed by KO, right? Same argument. Those are angles opposite equal sides of a triangle. No problem. So what we're trying to do here, we're trying to prove that this angle is equal to twice the angle of that. Right? We're trying to say the angle here is equal to twice the angle K. That's what we're trying to do, because the angle O is equal to twice the angle K. So now, we must find the magnitude or expression of angle O, right? But if you look at the red triangle here, the red KOT, you can see it has an exterior angle here, right? This is the exterior angle of what? Of KOT. So, because we're trying to express this angle as in terms of K, we must also define this angle here and that angle there, so that we can have the entire size of TOP. Because that's what we're trying to prove in the first place. TOP is equal to twice TKP. So we need to express to find the value of this and find the value of that. So I'm going to attempt to try to find the value of this angle O here, which is TOD. So this angle here is an exterior angle of the triangle, because you know from analytical geometry, if you have, let's say, you have this situation here, and you have a triangle here, this angle here is called the exterior angle, this angle here. It's the exterior angle. And it's equal to the sum of the interior opposite angles, which means you have to add this angle and that angle to find the magnitude of the exterior angle. So this is the same situation. This angle here is an exterior angle of the red triangle. So if you want to find the size of this exterior angle, you must add the interior opposite angle. That's what you need to do. Because the exterior angle of the triangle is equal to the sum of the interior opposite angle of a triangle. So if you want this angle, which is TOD, on the red triangle, so I'm going to use the red color, I'm going to say my TOD is equal to what? Is equal to this angle plus that angle. We already have those angles to be OTK and TKD. So it's going to be OTK plus what? Plus TKD, which is that angle over there. TKD. What is the reason for doing this? You say that exterior angle of a triangle, which is what triangle is, triangle what? It's triangle KOT. So your TOD, which is TOD, this angle here, it is the exterior angle of our triangle KOT. That's why we did this. TOD is an exterior angle of our triangle KOT. But look at this. We said this angle and this angle are equal. We said that then because we said those were angles opposite equal sides, right? And now what we're trying to do, we said want to relate O to K. So write your angle O in terms of K, right? So because this is also equal to K, you can substitute your angle K there as well and say, okay, my TOD is equal to TKD plus TKD. So you express this OTK in terms of K because you want your O to be in terms of K because you're trying to relate K and O here. So if you simplify this, say, okay, my TOD is equal to 2 times TKD Done with the green triangle. Now we move to we're done with the red triangle. We go back to the green triangle. On the green triangle, so what we have done actually here, we have expressed this angle O in terms of K. That's what we've done. This exterior angle, we've expressed it in terms of K. So what we have done it, we have to express this one, this DOP, this angle O on this side, the green angle, in terms of that green K up there. So this is what we're trying to find now. This angle out here. And you shouldn't be surprised. It is also an exterior angle of the green triangle. So what I'm going to do, you'll say, okay, what I'm going to do here, this exterior angle is equal to the sum of the interior opposite angles, which is this angle out here is equal to the sum of the interior or inside opposite angle, which means you must add this angle and that angle over there to find it. So what I'm going to do is, okay, my angle, which is this angle here, which is it's a green triangle. So I'm going to use a green color. I'm going to say DOP is equal to what? Is equal to that angle up there, which is angle K, which is DOP, which is also DKP, which is what we have here, right? Because we already defined this to be DKP. So we're going to have DKP plus what? Plus this angle here, which is KPO, which is KPO. What is the reason for using this? We're saying DOP is equal to this sum of this because DOP is the exterior angle of our triangle, what? KOP. So we're saying this angle here, DOP, is equal to the sum of these two because it is an exterior angle of this triangle KOP. No problem. But remember what we said here. We said these two angles are equal, which is these two that we're adding here are equal because they are angles opposite equal sides because they're both facing. They are in a triangle and they're facing sides of equal length, right? So both of them are equal. So now what we want to achieve, we want to express our angle O in terms of K, right? We want to express our angle O in terms of angle K there. So what we're going to say is, okay, our DOP is equal to what? DOP is equal to DKP, right? Plus DKP. So we've expressed angle O in terms of what? In terms of K. And then now you can simplify this and say your DOP, your angle O is equal to twice your DKP. Right? No problem. So once we're done with this, remember what we're trying to achieve. What we're trying to achieve, we're trying to prove that TOP is equal to twice that amount, right? So we're trying to prove that. I'm going to use a different color now. I'm going to say TOP is equal to, we're trying to say angle O is equal to twice the angle of K, right? So angle O, which is this angle here, you can find it by adding TOD and DOP. Because if you add these two angles, you get the entire angle TOP. So if you want your TOP, you must add your TOD and your DOP. So your TOP is equal to your TOD plus your DOP. No problem. But we do have this TOD. What is it? TOD is this red thing here. So TOD is 2 times. And okay, plus this angle here. DOP is this one, which is 2 times DKP. And this is equal to 2 times. Just factorize, factor the 2 out. So inside you're left with TKD plus plus DKP. No problem. So I'll continue on the other side. I'll say your TOP now. I'm continuing with that, the side, which was same, which is that, is equal to 2 times. So, your TOP, right, which is the TOP, or let me write it, rather. Your TOP, your angle O, is equal to 2 times TKD. What is TKD? TKD is this right angle here, plus DKP. DKP is that angle over there. So, what you are adding here, you are adding this green angle and the red angle, because TKD is this right angle and your DKP is the green angle. So, what you have inside there is the sum of those two angles. And the sum of those two angles, they form TKP, which is the entire angle. So, this inside here is your TKP. So, which means out here, you have your TOP to be equal to, which is what we're trying to prove in the first place. So, we're done with this question. So what do? Just say this. Done. So, now we're going to 8.2. They are saying, in the diagram, O is the center of the circle. A, B, C, D is a cyclic quadrilateral. OB and OD are drawn, right? If O1 is equal to 4x plus 100 degrees and C is equal to x plus 34 degrees, calculate giving reason the size of x. So, we're given this circle here, right? And then we're told that O is the center of the circle, right? And A, B, C, D form a cyclic quadrilateral. They're saying your OD and your OB are drawn. So, they said now, if O1, which is this angle here, is equal to 4x plus 100 degrees, and this angle C is equal to 34 degrees, calculate giving reasons the size of x. Okay, no problem. So, we're told that A, B, C, D is a cyclic quadrilateral, right? So, they're saying A, B, C, D is a cyclic quadrilateral, cyclic quad. What is a cyclic quadrilateral? Of course, as you might guess, what is a quadrilateral to begin with? A quadrilateral is a four-sided shape, right? That's what you are dealing with at your level, at least. That's what I would say. It's a two-dimensional, four-sided shape. That's what I would say. So, I'll say a cyclic quad. A cyclic quadrilateral. Oh, sorry. So, a quadrilateral is a two-dimensional, four-sided shape. That's how I would define it, just a quadrilateral. Then now, when you say it's four-sided, of course, it has four vertices. So, for example, something like this is four-sided, right? It has four sides. And of course, it also has four vertices. So, this is a quadrilateral. This is an example. For example, a square, a rectangle, a parallelogram. Those are examples, maybe a trapezium. Those are examples of quadrilateral because they are four-sided. Then now, if you're saying your quadrilateral, which is a four-sided shape, is cyclic, which means all the four vertices, which is this vertex and this one and that one and that one, you say your quadrilateral is cyclic if you can draw a circle that connects all of those vertices of yours. For example, let's say I have a point, a point, a point, and a point. And I draw a circle. Let's say this was a nice circle. This doesn't look very nice. All of these vertices of mine lie on this circle, on the circumference of the circle. Which means this is the cyclic quad. So a quadrilateral is cyclic if you are able to draw a circle that will go through all those points with its circumference, if that makes sense. So here you have a cyclic quadrilateral, which means this point and this point and this point and that point, all 4 points, they lie on the circumference of the circle. That's what it means to be a cyclic quadrilateral. No problem. What else do you know about the cyclic quadrilateral? You know that if you have a cyclic quad, let's say, I'll draw it again, I shouldn't have cleaned it. If you have a cyclic quad, A, B, C, and D, if you sum opposite angles, interior opposite angles, they are supplementary. They add up to 180 degrees, right? Which means if you say your angle A plus your angle C, they will give you 180 degrees. And these angles here, angle B, angle D plus angle B will give you 180 degrees. Which means interior opposite angles of a cyclic quad are supplementary. They add up to 180 degrees. That's the second thing that you need to know. And the third thing is that if you this is still your cyclic quad. Let's say now we have an angle out here. It's called an exterior angle, as you know from the previous question. This is an exterior angle. An exterior angle of a cyclic quad is equal to the interior opposite angle. So this angle here will be equal to this interior opposite angle. At this point, this is all I need to tell you about cyclic quad in order to be able to approach this. I will not dwell much on this. This will be enough. In fact, it's more than enough. So let's go to the question. So in this case, we're given the cyclic quad A, B, C, D, right? And we're told that O1 is equal to 4x plus 100, which is O1 is this angle here, right? It's equal to what? 4x plus 100 degrees. Also, we're told angle C, which is this angle over here, we're told that this is what? Is x plus 34 degrees. So you're given these two angles. So they want you to find the value of x. So you use the information that you know from Euclidean geometry in general. What you know is that it's your minor arc dB, which is this small arc here, which is this arc dB. You can see it. Let me just do this. This minor arc dB subtends this angle here, which is this one, this 4x plus 100. It subtends this angle 4x plus 100. And the same dB subtends angle A at the circumference. So dB subtends O1, which is this angle here, and subtends angle A at the circumference. So you know that the angle subtended at the center is twice the angle subtended at the circumference, right? Which is the angle that dB is subtending here will be equal to twice the amount that it subtends at the circumference. So what you can say, okay, my angle O1 is equal to twice the angle of A. What is the reason for that? You say angle at center is equal to twice the angle, is equal to two times angle at the circumference. So O1 is equal to twice angle of A. Right? So you have your O1 to be that. You know that it's going to be twice the angle of A. Why? Because the angle at the center is equal to 2 times the angle at the circumference. So which means your O1, you have your O1 to be what? To be 4x plus what? Plus 100 degrees is equal to 2 times angle A. Then divide by 2. Divide by 2. You get that your angle A is equal to 2x plus 50 degrees. That's your angle A. So you have this angle here to be equal to what? 2x plus 50 degrees. From that, because you said the angle subtended by an arc or a chord at the center is equal to twice the angle subtended by the same chord or same arc at the circumference, which is what you've done there. No problem. But then we also know that ABCD is also a cyclic quad. So what does that mean? We can say with confidence that angle A plus angle C will give 180 degrees. Why? Because they are opposite angle of a cyclic quad. Because I said the opposite angle of a cyclic quad are supplementary. So what we'll say now, we'll say, okay, we know that if we add angle A plus our angle C should give us 180 degrees. Why? Those are opposite angles. These are P's. Opposite angles of a cyclic quad. That is our reasoning for that. We know that if we add angle C and angle A should be giving us 80 degrees, 180 degrees, because those are angles of a cyclic quad. And I said the opposite angles of a cyclic quad are supplementary, which is the add up to 180 degrees. But we know angle A is equal to 2x plus 50, and we know angle C is x plus 34, then they add up to 180. So what we can say, we can substitute our A here, which is what? Which is 2x plus 50 plus C, which is what? Which is x plus 34. Is equal to 180 degrees. Just substituted from this. So these are degrees, of course. So you have 3x plus 84 degrees, right? It's called 180 degrees. Then your 3x is called 180 degrees minus 84 degrees. So your 3x is equal to something like 96. And then let's see, then you divide by 3 and you divide by 3. Then you use your calculator from there. So what you say, so you say your 96 divided by 3. You get that your x, is equal to 32 degrees. And we're done with this question. We're done with this question. This was 8.2, not 8.1. We're done with 8.2. Then we'll move to the next question, which I believe is the last question of question 8, which is 8.3. I'll clean the board and then we'll go to 8.3. So now we're doing 8.3. So 8.3 reads as follows. In the diagram, O is the center of the larger circle. OB is a diameter of the smaller circle. Chord AB of the larger circle intersects the smaller circle at M and B. So we're given this big circle and this small circle that you can see here. They are saying that O, which is this point here, O, as you can see, it is the center of the larger circle, right? And you are told that OB, which is this length that you can see here, it is a diameter of this smaller circle, right? So OB, which you can see here, which is OB, which is this, is a diameter of this smaller circle that you can see here. And they also want them to say that you have a chord AB, right? They are telling you that it intersects the smaller circle here at M and there at B. I will repeat this thing again. You have a larger circle, here is it. And you're told that it has a center at O, which is that over there. You have a smaller circle, which is this one here. And you're told that it has the diameter OB. No problem. Also, you have this chord AB of the larger circle. And you're told that the chord AB of the larger circle intersects the small circle at M and at B. That's what they're telling you. That's what we get from the statement. No problem. Let's continue. Now we're going to 8.3.1. They're saying now, write down the size of angle M and provide the reason, which is OMB. They're saying, write down the size of OMB. They want OMB, which is this angle here. OMB. So they want this angle here. They are asking, what is the size of this angle here? And provide a reason. Right? No problem. So, you know very well that if you have a circle like this, right? And you have a diameter of yours here. So, the diameter of yours, the angles on a diameter add up to 180 degrees. Right? The angle on a diameter, they add up to 180 degrees. So if you subtend anywhere on the above half a circle, or it doesn't matter which side. If this diameter subtends anywhere on this half a circle, on this semicircle, all the ends will be half this one. So they will be 90 degrees. That's what you need to know. Because you have a circle and you have this diameter. I'm telling you that this is a diameter. This one is a diameter. So I'm telling you, angles on a straight line add up to 180 degrees, right? You know. And then, which is, you have 180 degrees on this diameter of yours. So if this diameter subtends an angle on, let's say now, let's focus on the upper side, which is if it subtends anywhere on this half a circle or on this semicircle, the angle that it will be subtending will be 90 degrees, because it will be half the angle subtended at the circumference. Because you say the angle at the center is twice the angle at the circumference. So that one is half that is subtended at the center, which is at 80 degrees. So in that case, you say that this point, these 2 points, they subtend 180 degrees here, and they subtend half of that at the circumference or on the half a circle. Doesn't matter which side, can be this side. So in that case, here on this smaller circle, you have a diameter here, and this diameter of yours is subtending that angle over there. So the angle that is subtended by your diameter, it should be 90 degrees, because this point OB, they subtend what? They subtend 180 at the center. So they should be subtending what? 90 degrees at the circumference of the circle. So your angle OMB is equal to 90 degrees. Why? Angle in the half a circle, semicircle. That's the reason. The angle M is equal to 90 degrees. Why? Because the angle in half a circle. Because I said that in half a circle, if your diameter, because this is half a circle, which they call the semicircle, right? So if your diameter subtends anywhere on that semicircle or on that half a circle, it will always subtend 90 degrees. So I think we're done with this one. Then we move to the next one, which is 8.3.2. What are they saying at 8.3.2? They're saying now, if AB is equal to the square root of 300 units and OM is equal to 5 units, calculate, given reasons, the length of OB. So you are told that your AB is equal to the square root of 300 units, right? And your OM is equal to 5 units. So they want you to find OB. This is what they want you to find, OB. So what you have is this length over here, AB, from A to B, is this length over here. It's 300, the square root of 300 units. This length over here. Square root of 300 units. This is the length that you have. The whole length of AB is 300 units. And you're told that OM is 5 units, which is this length from the center to this is 5 units. So what do they want? They want you to find AOB, which is this length over here. They want to find the diameter of this circle. No problem. But it's easy to see that if you're looking at OMB, triangle OMB is a right angle triangle. So we can be able to use Pythagoras, right, to find that side. But we would need to have this side in order to use Pythagoras to find that side. Right? No problem. But look, you said this is 90 degrees, right? And a line is drawn center perpendicular to your chord. Right? You say that a line, you know that a line drawn perpendicular from the center to the chord, or a line from the center perpendicular to the chord, it bisects the chord, which is it splits it into two equal parts, or intersects at the midpoint of that chord. So M here, this point of yours, is a midpoint of this chord. So which means your MB is equal to AM, because a line drawn from center perpendicular to the chord will bisect the chord, because this line is drawn from the center and it is perpendicular to your chord. Therefore, it bisects the chord. It splits it into two equal parts. So what we can say from here, we can say, okay, we can say that AM is equal to what? It's equal to MB, right? AM is equal to MB. How do we know that? Because we say a perpendicular line from center to chord. We know it bisects the chord. From a perpendicular line from center to chord bisects the chord. So these two are equal. So if this is square root of 300, so this is half of it and this is the other half. So we say now your AM equal to your MB is equal to the square root of 300 divided by 2. That's half of that. No problem. What is your square root of 300 divided by 2? It's 5 root 3. Right? So we get that this is 5 root 3. No problem. So we have this length to be 5 root 3, and we have this length over here to be 5 root 3. So look, you have your right angle triangle. You can use Pythagoras to find OB. What do you say? You say your OB squared, right, is equal to what? It's equal to OM squared plus the square of MB. So what you say, this reason for this is Pythagoras theorem. No problem. So your OB squared is equal to your OM squared. What is your OM? You're told that it's 5 squared plus your NB squared, which is 5 root 3, right? It's 5 square root of 3 all squared. So therefore your OB is equal to, so that say your 5 squared plus 5 root 3 all squared, and then take the square root of that, we'll find that this is 10 units. So that is the length of your OB. And I think we're done with this. And I hope it does make sense to you as it does to me. Thank you for watching. Cheers.